Welcome to Electronic Specifier Insights, the podcast for electronics engineers. I'm your host, Paige West. In today's episode, I speak with Dr Josep Montanyà y Silvestre, CEO at Nanusens. We speak about their patent-pending technology enabling MEMS nanostructures to be built within the layers of a CMOS chip using standard CMOS processors. This enables them to create both MEMS sensors and MEMS capacitors with the required control circuitry as innovative single-chip solutions that are significantly smaller than their current multi-component equivalents. I hope you enjoy this episode. Let's get started. Today, I am pleased to be joined by Dr. Josep Montanyà y Silvestre, CEO of Nanusens. So thank you very much for joining us. Why don't you start by telling us a little bit about yourself and your background?
Good morning, Paige, and thanks for inviting me. So my background is telecommunications engineering, and I made my PhD in MEMS, in microsystem technology, both at the UPC in University in Catalonia, Spain, in Barcelona. And I've been working in making MEMS in the backend of CMOS for the last 20 years, actually. So I started a company developing this 20 years ago, and Nanusens back in 2014.
Fantastic. So tell us a little bit more about Nanusens then.
So the vision for Nanusens is to make MEMS devices using standard CMOS processing. So MEMS has been there for many years, and today is a big industry. So initially there were commercial applications in automotive industry. Then later, when Steve Jobs used an accelerometer into the first iPhone, there was a start of a boom of MEMS consumption into smartphones. And today, MEMS are used in many places, in wearables, in all kind of industries. But still, it's like a niche technology, while all the solid state chips are being built using a de facto standard, which is CMOS. For MEMS, each vendor has its own bespoke manufacturing process, so there's no standardization. And this is a problem because the economy of a scale is limited, and it's not possible to reduce costs, to increase performance, to make the chips smaller, which is what the market is demanding. So the vision of Nanusens is to make the MEMS using the standard CMOS processing exactly the same as the solid-state chips. So this way, we can build MEMS devices with unprecedented levels of miniaturization, very low power consumption, lower cost as well, higher performance, and very large volume production. So it's a big disruption into the semiconductor industry, because we are joining these two types of chips with electronics and chips with mechanical parts inside.
Could you explain for us what sets your MEMS and CMOS technology apart from traditional MEMS manufacturing approaches?
Yes. So the approach we follow at Nanusens is that in order to be able to make the MEMS in CMOS, it's two things. First, we apply post-processing. We build the CMOS wafer, and then we apply hydrofluoric acid in vapor stage to the wafer. And what this does is that it removes some of the silicon oxide inside the wafer. So it creates the empty spaces that are needed to enable a mechanical movement. And then it's the metal layers that are already there, in principle, to make electrical connections, but we use them for different purposes. We use them to make a mechanical movement. And that is our approach. What other companies do is a completely new process. So they start with a blanket wafer. Typically, they deposit many layers to make the mechanical devices. We are not adding materials to the wafer. We are just reusing what we have there using the standard CMOS. And that's our unique approach.
And what types of MEMS structures are currently possible within standard CMOS layers? And what are the limitations, if there are any?
Yeah, so with this approach, we can make many different types of MEMS devices. We can make sensors, for instance, inertial sensors like accelerometers, gyroscopes, pressure sensors, microphones, magnetometers, ultrasound devices, gas sensing, infrared imaging. All these are sensors that we can build with our approach. We can also build actuators like radio frequency digitally tunable capacitors. This is actually going to be our very first product that we'll launch to the market, and it's needed for 6G phones to tune the antenna properly. There are even other devices, that we are developing, like digital processors. We can build equivalent to the all thermionic bulbs, the vacuum tubes built in at the nanoscale, which has the advantage of enabling very fast speed transfer of electrons because they don't have to go through the silicon, but they can be literally flying in vacuum. So there's many different devices. I would say that most of the MEMS devices that you need for consumer, we can make them, but we do have our limits. So the limits come because we do not choose the materials. We don't have the luxury of being able to choose what materials we use and what properties of these materials. It's whatever it's there in the CMOS. This means that when it comes to optical devices, to biocompatible devices, and also in terms of clocks and timing, for now, maybe it changes in the future, but for now, we don't see how to get into those devices for this reason, because we cannot change that, and sometimes we would like to change it, and internally in our engineering meetings, it's like, oh, if we could modify the process and add this layer with this material, but it's no, stop. I mean, our mantra is we don't change the process because it's a temptation we have all the time, but as engineers, But I know that if we make any small change in the process, then it's not standard CMOS anymore. So then we would lose all our advantages.
I'm interested to hear, following on from that, what have been some of your biggest technical challenges in developing MEMS structures within CMOS, and how have you overcome them?
Yes, the big challenge is that we are using materials with mechanical properties that are far from ideal. So, I mean, the usual approach in MEMS is, if you want to make a MEMS device, be it an accelerometer, pressure sensor, microphone, whatever, you design the device and then you design the manufacturing process. That's what everybody else is doing. And it's relatively easy then, say, to design the device. It's more challenging to design the manufacturing process, because if it's for consumer and you require high volumes and high yields, that's very challenging. And if it's a startup, many startups die in that process. Our approach is the opposite. We started with the process. It has to be CMOS with vapor HF post-processing, and then we've been many years figuring out how to make a design that fits that. So in particular, we are using the metal layers of the backend of the CMOS process. They are thin. They have large residual stress. They have large vertical stress gradient. When you release them, they bend. So it's totally opposite of what you try to achieve when you have your own process. So that's why it's been so many years trying to find out the right design techniques to use these materials, which in principle, they don't have the right mechanical properties. What we've discovered, however, is that in addition to these challenges, there were a number of advantages. So in particular, using this approach, because it's in CMOS and it's a budget process, we benefit from very small feature sizes, so very small gaps. We benefit from very low parasitic capacitance to connect the ASIC with the mechanical part, with the MEMS. And we also have the luxury of using a large number of structural layers. So combining these advantages and the challenges is how we've managed to find the right design techniques. Now we know how to make that after 20 years working on this and destroying many wafers, many trial and error. And we've been building a strong patent portfolio to protect all that. But yeah, that's the main difficulty, to use a process that was not intended to be used for this.
So how does embedding MEMS directly into the CMOS layer impact performance in terms of things like power consumption, latency, and size?
Yes. So we can achieve better performance contrary to what someone might thought initially, because some people says, oh, it's in CMOS, it's metal layers, it's not the right mechanical properties. In reality, we can achieve better performance. And the key points are these advantages that I mentioned. So we can afford to have very small gaps, very small distances. That's important because most sensors at the end, it's a mechanical movement, and then you detect this movement with a capacitance sensing. No, imagine an accelerometer. You have a proof mass that moves based on the external acceleration, and then you want to detect that movement, checking the capacitance against a fixed electrode. So if you have a given movement and you have a large gap, it's going to be very challenging to detect that movement. If the gap is very small, the relative gap, so the relative capacitance variation is going to be much larger. So this means that you can improve sensitivity. And if you improve sensitivity, it's well known that you can always trade sensitivity by power consumption. So if you can improve sensitivity, you have the option to keep sensitivity and reduce power consumption. So we can achieve lower power consumption with that. Not only that, we can also achieve faster response. You talk about, if you talk about latency, bandwidth, all the time in metrics, having smaller gaps allows us to have better performance on this front.
Mm. And when do you expect to go to market with this technology, and what markets are you going to look to target first?
Yes. As a company, we are not developing a single product. We've developed a technology that allows us to make so many products. And I have to say that it's been quite challenging internally to find the best product market fit. No? And there are so many things that you can do that it's been always a temptation. Okay, let's try this, let's try that. But at the end, we need to focus. No, we are still a small company and we need to focus. The very first product we are taking to the market is a radio frequency digitally tunable capacitor. This is a device that will go attached to the antenna of 6G phones. So the antenna of smartphones nowadays is placed inside the phone, so it's affected by the hand, your head, the body, etc. So it needs a circuit called antenna tuner that is continuously tuning the radiation parameters of the antenna. This is something that all phones have. The problem is that and it works well, no? But when you increase the frequency above 2 gigahertz, it starts heating up because it's made with solid state. And for 6G, with frequencies above 5 gigahertz, you cannot do that with solid state. You need a MEMS device. No? It's instead of simulating a capacitance change with solid state, you need a real mechanical device that changes, no, the internally, and this does not heat up. And that's something that only Nanusens can build, because although there are other MEMS companies that have digitally tunable capacitors for smartphones, you not only need performance, you also need low cost, small size, extreme reliability, and high volume production manufacturing. With all these challenges, Nanusens is the only company that can do that. So we are targeting to have our first design wins and start selling in volume by 2028. Which is when we expect first 6G phones to hit the market.
And speaking of smartphones, how does the mobile phone industry benefit from reduced sensor footprint and lower energy consumption?
This is something really key, not only for smartphones, but for all kind of wearables and portable devices in general. So the big demand is more autonomy. So you want more time between recharges, and you want to add more and more functions. So reducing the size of the electronics means that you have more space available for your battery. No? And that's something really key for your battery and also for the antenna to enable better radiation, but especially for the battery. And then for wearables, beyond the smartphones, earbuds, smart rings, it's smaller and smaller, no? So it's really key to be able to make sensors and RF devices as small as possible. And that's an area where we can reduce the size to levels that nobody else can do. In fact, with our technology, the sensor chips can disappear because we can just embed them inside the digital processor. So it's infinite reduction, no?
Yeah, fantastic. And can you tell us more about how your approach is helping solve key RF front end challenges for 6G?
Yeah, so in 6G, you have several challenges at the RF front end that you need to solve. first of all, it's higher frequencies. You want lower losses, and especially you want higher linearity. So you cannot afford any small distortion, no, in all the devices there. So if you use solid state, combining low losses, high linearity, high frequencies, and the fourth one is high voltages, no, because the devices that are touching to the antenna, depending on which point at the antenna you are touching, we are talking about peak-to-peak voltages up to 160 volts, which is like, well, do we have 160 volts in our phone? Well, we do have, no? I mean, it's inside, so it's safe. But for the devices that are touching there, that's a lot of power for extremely tiny device of 100 nanometers. No? So all these are big challenges that need to be solved.
I'm interested to hear, given all you've said, how do you see the MEMS market evolving over the next 5 to 10 years?
So the vision we have for MEMS market is that there's going to be a radical change going from what we have today of separate technologies, bespoke manufacturing processes for each of the sensors. So if you want an accelerometer, you have one process. If you want a microphone, you have another process. Well, not one, several processes, one for each vendor. We need to transition from that to building them in CMOS, like another electrical block, no? And there was a similar evolution with solid-state electronics. I mean, CMOS was not there from day one, no? But then at some point there was a convergence. So with MEMS, it needs to be the same. And rather than being separate chips, you know, the strange chips that are there, they will become mainstream. They will be used in all ICs, and they would just be another IP block within the chips. That's our vision, no? And that's where Nanusens is going to enable that.
And looking back at your journey in this space and founding the company, what have been some of the key lessons that you've learned?
On a personal level, many lessons, many lessons. You know, sometimes I think that if I had to start again, probably I would try to advance more the technical part within the umbrella of a university. So rather than just starting a limited company with private funding from the idea on a piece of paper, which is basically what I did, then it's very challenging, you know, to fund the R&D with private funding. If you set up the company when you have, you know, a prototype within the university, then on the fundraising side is more easy, but it's always difficult to say, because sometimes I think, well, maybe if I had done that, it would have been more difficult for me to learn about the real market, because that's something that I've seen also. Usually most universities, well, I would not say all the universities, it depends on the country and the university, but many universities, I see that they have deep technical knowledge, but there's usually a strong disconnection with what's really needed in the industry, no? But maybe I would try to make a spin-off. And then in terms of the structure of and governance of the companies, I've been learning about the importance of maybe not having one single shareholder, you know, having more than 50% of the company, the importance of having the right shareholders, the right board directors. Sometimes you only think about the team, but the board of directors is super important as well. Yeah, there's lots of things.
And where would you like to see Nanusens in, 4 or 5 years' time?
So in 4 or 5 years' time, Nanusens will have IPO'd, and it will be the reference for MEMS devices. So our IPs will start being used widely in most ICs, no? And it will be the reference company for MEMS and NEMS technology.
Fantastic. Well, I'll have to speak with you again in 5 years' time, and we can chat about all the successes that you've had.
Sure. Yes, of course.
Brilliant. Well, thank you very much for taking the time to speak with us and for introducing Nanusens and your technology. It's been a real pleasure hearing your insights, so thank you very much.
Thanks, Paige. My pleasure.
Thank you for listening to this latest episode of Electronic Specifier Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.